Hello guys, welcome to this video. So in this video we're going to continue what we started in the last one, that is about the Riemann zeta function, the Bessel's problem, and the infinite series that were concerned with the integral, which was 0 to 1 ln of 1 minus x by x dx. So we were trying to investigate about this integral in the last lecture, and what we saw was that this integral resulted in an infinite series, which was basically the sum of the reciprocals of the squares of the natural numbers. That is, they started from 1 and they went up to infinity, and we somehow knew that that infinite series is going to be pi square by 6 from literature, but we do not yet have a proof of that. And since the proof is a bit advanced, I would try to make things as easy for you as possible, and for that I might need to quote some results without proof as well, because not everything can be proved, because it is not really a lecture where we prove these identities. It's really a supplementary course of calculus for probability. But what you should know about a few things is infinite series, how to handle them, how to handle integration and stuff, right? Okay, so let us begin by understanding that this series was turned into this integral was turned into this series, right? Negative of n equals to 1 to infinity 1 by n square. Now why is it a negative sign in front of it? Because obviously if you see in between 0 to 1, that is for all x belongs to 0 comma 1, what we have is ln of 1 minus x is less than 0. Because see, if x is belonging to 0 comma 1, then 1 minus x also belongs to 0 comma 1, and that is why ln of something, so the argument, if the argument of a logarithm is like between 0 and 1, it will always be negative, right? So arguing to this, the numerator is always negative while the denominator is always positive, so a negative number divided by a positive number will always result in a negative value, and thus integrating over the whole interval we add a bunch of infinitesimally small negative values which will result in a negative answer. So that is why the integral is negative. Now the question remains how to find this series. Now let us try to understand the various ways we can do that, but the way I'm going to show you is by factorization of sin x. Factorization of sin x. Now this is a result that I'm going to quote without proof, but then again this proof can be done later in the algebra section when we are trying to understand different kinds of polynomials that can represent different functions. So that is called interpolation, where a function can be represented as a polynomial, maybe an infinite one, so the degree isn't defined, but still interpolation helps you to make polynomials for a bunch of functions. It is also called regression in statistics. So what is the factorization of sin x? So long ago what Euler did was find out that the factorization was sin of pi x by pi x equals to infinite product r equals to 1 to infinity 1 minus x square by r square. So this basically was the idea. This was his idea of making the infinite product for sin of x, and this idea had to do with the fact that I'll just give you an intuition on how this works, because as you can see, sin of pi x equals to 0. This equation has roots on the real numbers, on the natural numbers, right? Both positive and negative, so plus minus 1, plus minus 2, plus minus 3, and all the way up to infinity including 0. So what he did was he thought that if sin of pi x were to be, and not like that, if sin of pi x were to be a polynomial, well, according to the fundamental theorem of algebra, it would be something like x into x minus 1 and stuff like that. But what he did thought was that obviously this equipped with x plus 1 and everything else would give you something like x into 1 minus x square into 1 x square minus 1 into x square minus 2 square, and so on, right? And he also said that there would be some function g of x in front of this extract thing. So what he did was he told that sine of pi x should be equal to some function g of x multiplied by x multiplied by x square minus 1 square, x square minus 2 square, and so on. So that g of x was such that it turned out to give this function. So it was proved later, but Euler had guessed it correctly but not proved it correctly. So regardless of that, we know the factorization is this. So let us make use of that. So from the factorization, we have that so if you see that we have sine of pi x equals to pi x into 1 minus x square by 1 square, 1 minus x square by 2 square, and so on. So the coefficients here are something like this. So obviously the ones will multiply out itself to give you a pi x when you expand this whole product. So pi x is one of the terms of the expansion of this product, right? Now what would be the coefficient of x cube, because there is no x square, remember, because there is always a x and all the terms are quadratic, right? So one possible coefficient is x cube and another possible coefficient is x square into x, which is x to the power 5, and so on. So the coefficient for x cube would be minus x cube whole into pi by 1 square, and so all of these terms would be added, right? All the negative terms involving x square but multiplied with x, plus pi by 2 square, plus so on, and then you have all the rest. So this is one of the expansions for sine of pi x, right? Now if you recall correctly, we recall from Taylor series that sine of x is simply equal to n equals to 0 to infinity minus 1 whole to the power n x to the power 2n plus 1 by 2n plus 1 whole factorial. So if we were to just write it as an infinite series, what you would get is something like this: x minus x cube by 3 factorial, and so on, right? So yeah, this both of these series must be equivalent in representation, or at least their coefficients of the terms of the coefficients, because as you can see, here is x, there is an x cube, there is x, there is an x cube. There is also a series where you have odd powers of x, and so is this series, right? So obviously equating the powers of x cube, but first we need to find out what is the Taylor series of sine of pi x. So simply put pi x instead of x to see that this is pi x minus pi cube x cube by 3 factorial, and so on. Now comparing the coefficient of x cube, comparing the coefficient of x cube, we have, so in that we had pi by 1 square plus pi by 2 square and all the way up to infinity equals to minus pi cube by 3 factorial, right? So here we can write it as minus pi into summation n equals to 1 to infinity 1 by n square equals to minus pi cube by 6. So if you cancel the minus pi's, what you get is pi square. Therefore n equals to 1 to infinity 1 by n square is just equal to pi square by 6, which is the answer that we seeked. So you see that this kind of problems are not really very trivial, so you cannot solve them by any means that you have learned in school or college. So These are creative problems and this require creative solutions. Think of all the mathematicians that have come before us and how they solved it, how they thought of it in the first place. So it was very unique, and obviously a bunch of things were used here, like the factorization of sin x, then the Taylor series of sin x, of course, and we had to equate them and we magically get this answer. In a similar fashion, just to note, the following series also has a value 1 by 1 to the power 4 plus 1 by 2 to the power 4 plus 1 by 3 to the power 4 and all the way up to infinity. This series has a value of pi to the power 4 by 90. Believe it or not, but this can also be proved very easily, which is something we shall keep for other lessons. So I think this would be it for this lesson, because there is nothing much to be done in this one. But obviously in the next lesson we shall see some more integrals related to the ones that we have done here, like 0 to 1 log of 1 minus x by x. We can see some variants of this integral, then generalize some of the things and do some more integrals, and then we can move on to our actual topic, which is continuous random variables, and move forward in probability. So anyways, thank you for watching and I shall see you in the next video. Do download the Breatter Math app, which the link is in the description of the video, and you can download it. You can see all the related video solutions, this video and its related theory, all of that in that app. And you also have bunch of statistical calculators and probabilistic calculators where you can do derivative integration, find probabilities and stuff. So do check it out, and thank you for watching.